Chapter 6 of our course concerns itself with thermodynamics. Thermodynamics literally means heat movement, thermodynamic. Now we know from high school science that heat is a component of energy. Energy itself can be broken down into two different types: kinetic, which is the energy associated with motion, and heat is directly related to that motion, and also potential energy. And potential energy is an energy that is imbued into an object because of its position. And in chemistry, those are going to be our chemical bonds. So I have two types of energy within a chemical system: the energy associated with motion, or heat, and then the energy associated that is trapped inside the chemical bonds. All that energy is the ability to do work or to transfer heat. And work is defined as the ability to move against an external force. Energy is going to be measured in joules. Joules are our SI, Standard Institute unit for energy. But there is another very, very useful unit of energy out there, and that is the calorie. Now, we don't technically use the calorie that much, although it is in widespread general public use. It is a wonderful little definition. A calorie is the amount of heat required to raise 1 gram of water by 1 degree Celsius. That's a very, very tight definition, which allows for easy experimentation. And there is a conversion factor that a calorie is 4.184 joules. That number's going to come back later on. Thermodynamics is governed by laws. In fact, there are 4 laws of thermodynamics. The first law is a restatement of something in physics called the law of conservation of energy. You might be aware from high school science that there are 2 laws, one called the conservation of mass and one called the conservation of energy, that tell us that in any process you cannot create new mass, new matter, and you cannot create new energy. So the conservation of energy says energy cannot be created, nor can it be destroyed, but it can be moved from one place to another place, or it can be moved from one form to another form. In the same way that an engine converts heat into motion, it converts thermal energy into mechanical energy. The change in total internal energy for any given system is equal to the heat minus the work. And you can get lost in that. We'll keep that to a minimum, but there is a point in some biological systems where we need to consider that some form of work is being done. The second law of thermodynamics, which is ever so slightly outside the scope of Chemistry 1, tells us that heat always travels from a hot object to a cold object. So on a cold wintry night, if you leave the front door open and somebody yells, "You are letting the cold in," no, you're not. You're letting the heat out. Heat always has a direction, and it flows from hot to cold. As chemists, we're interested in knowing what the energy change associated with the chemical reaction is. And for that, we rely on something called enthalpy change. Enthalpy is just the German word for heat. But the distinction here that's important, and the textbook does not do a good job at this, is that we only want to know the change in the number. So every time, except for the very first time when you read it in the textbook, when it's defined for you, every time it says enthalpy, what the book really means is enthalpy change. Enthalpy is the German word for heat, specifically a heat exchange at constant pressure. Now, when you consider that most of the reactions that we're going to be interacting with are done in solution, in a liquid, they're all going to be at atmospheric pressure. So almost everything that we do is done at constant pressure. So the enthalpy change is the heat that is evolved or absorbed during a chemical reaction or process at constant pressure. And that gives us two scenarios. If I were to plot energy versus time, my chemical reaction might start out that my reactant was higher in energy than my product. And so over the course of time, energy is lost. Where is that energy lost to? Because energy cannot be destroyed. It's lost to the surroundings, to the environment. In this case, this reaction is exothermic. Energy as heat is given out to the surroundings, and our value of enthalpy change has a negative value. Remember, heat has a direction. Our other scenario is that our reactants are lower in energy than our products, and that over the course of time, energy is taken in to make the reaction work. This is called endothermic. Heat energy is taken in during this process or reaction, and our value for enthalpy change, delta H. Anytime you see a delta in the book, the capital Greek delta means change. If it's a lowercase delta, that means just a little change. The value of delta H is positive. Now that leaves us with the question mark of exactly what's happening in between, in the space between where my reactant is and where my product is. And you might think, nature being what it is, to do the easiest thing and just draw a straight line between these two. But that cannot be true. Observably, that cannot be true. Because if we turned reactants into products by giving them energy, when we took that energy away, wouldn't they all just go back to being reactants again? So there's something else going on in the middle. It's something that required discovery, and it turns out that the reaction profile looks something like this. That in order to make a reaction work, you have to put a little bit of surplus energy in first. You do get that back out. And so there is this hump in both cases. So that hump in the reaction profile has a name. It's called activation energy. It's given symbol EA, and it is the absolute barrier to reaction. Below this energy, the reaction cannot occur. So to go from reactants to products in an exothermic reaction, I have to give my reactants some energy first to force them to react. That energy will be given back to me, and then I generate the product. So there are two new arrows on this diagram. The first shows us the magnitude of the activation energy. It is the gap between the energy of the reactant and the maximum energy in the profile. And then I have this blue arrow, which is the enthalpy change. It is the gap in energy between reactant and product. And this gap is pointing downwards. In an endothermic case, I have to go very high for my activation energy because the activation energy has to be higher than the product. But I get some of that energy back. Here the green line represents the activation energy. The blue line represents the enthalpy change. Again, it is the gap between the reactants and the products. In this case, it is energy being taken in. So energy and enthalpy change has a sign. If I were to take this reaction and perform it backwards and turn my products back into reactants, the enthalpy would reverse itself. We measure the amount of heat being given out or taken in during a process or reaction using an experimental technique called calorimetry. And the basic equation of calorimetry tells us that heat in joules is equal to mass in grams times something called the heat capacity times the change in temperature in degrees Celsius, which is really Kelvin. Now, heat capacity is the amount of heat required to increase 1 gram of the material that we're looking at by 1 degree Celsius or 1 Kelvin, which means that if I change the substance, if I change this from copper to lead, I've changed the nature of my material. So heat capacity is specific to the material that you're looking at, why it's often called specific heat capacity. And heat capacity for reactions that are performed in solution just fall back on the value of water, because if you've got something in solution that's causing heat to be given out, well, what you're really doing is warming up the water that you're dissolved in. And here's that number again. The specific heat capacity for water is 4.184 joules per gram per Kelvin, or joules per gram per Celsius. The enthalpy change for a reaction is heat per mole. So we just take the number from the calorimetry experiment and we divide it by the number of moles being used. It is possible to change the heat capacity in this equation into something called the molar heat capacity, which is a slightly different number. Enthalpy is something called a state function, which means that its amount only depends on the initial and final state of the process, not on the pathway that got you to that end point. Which brings us to Hess's law. Hess's law says that the total enthalpy change in any process is the sum of any smaller individual steps. So if I wanted to look at the enthalpy change for a reaction that took me from A to D, that would be the same as the individual enthalpy changes from A to B, from B to C, and then from C to D. Which seems like this might be hinting at more work, but it's actually going to make our life easier. Because what if this thing right here, the transition from B to C, was very difficult to observe? But A to B was easy and C to D was easy, and we knew what A to D was. We could calculate what that missing step is. And if our reactions can be written in a way that they go around in a cycle, then Hess's law tells us that the enthalpy change for a cyclic process has to be equal to 0. That if I start at A and I have to increase energy to go to B, so this is endothermic, and then I have another endothermic process to get to C, and then I have an exothermic process that goes to D, and then I have another exothermic process that goes from D back to A, then my entire process has an enthalpy change of 0. That the amount of energy put in has to be equal to the amount of energy given back out again. This is going to allow us to theoretically find numbers for processes that are difficult to find. And it's going to allow us to perform experiments on paper without having to do them in the lab. Hess's law hints that we might not have to do the experimental work for every single reaction, every single time that we perform it, because some of this information is already known to us. And that's where standard enthalpies come in. The enthalpy change at standard conditions of formation is the standard enthalpy of formation, which is the enthalpy change when a substance is formed from its component elements in their natural form at 1 atmosphere of pressure and 298 Kelvin, which is 25 degrees Celsius. So here's an example. Carbon as a solid, as graphite, that's how carbon exists in its natural form, would react with oxygen, which exists in its natural form as a gas, an O2 molecule, to make carbon dioxide gas. And we know that that's a combustion, and combustions generate heat. So this reaction will be exothermic. And it turns out that the standard enthalpy change of formation for this reaction is negative 393 kilojoules per mole. Well, that's already known, so it's written down in a table, in an appendix, in your textbook. So we don't have to do that reaction again. And now I can use this information to help me figure out other reactions. The enthalpy formation of any element under standard conditions is 0, because the elements already exist. You don't have to put any energy in or take energy out in order for the elements to exist. They already exist. So their standard enthalpy of formation is 0. So let's do a worked example where we find the standard enthalpy of a reaction. The standard enthalpy of a reaction is equal to the sum of all of the standard enthalpies of formation of the products minus the sum of all of the standard enthalpy of formations of the reactants. Okay, that might look a little intimidating, but let's break that down. Change, heat, standard. All the standard means is at 1 atmosphere of pressure at 298 Kelvin and involving materials and elements in their naturally occurring states. This squiggly sign right here means the sum of, which just means add the numbers together. N is the total number of moles. So if I were to do a reaction that had double the amount of one reactant than another, or double the amount of one product than the other, I have to take into account the number of moles that I'm looking at. And then we're looking at the standard enthalpies of formation of the products. Okay, let's look at the combustion of methane. Methane is a gas, and it's going to react with oxygen, that is a gas, in a 1:2 ratio to make carbon dioxide, that is a gas, and 2 molecules of water as a liquid. If I set my equation out now, the amount of heat that I should expect from this reaction is equal to the sum of all the enthalpies of formation of the products minus the sum of all of the enthalpies of formation of the reactants. My products are the enthalpy of formation of carbon dioxide plus twice the enthalpy of formation of water. Subtract from that the enthalpy of formation of methane and 2 times the enthalpy of formation of oxygen. Now, all of those numbers that we're going to put into this equation are available in the textbook. They're tabulated in Appendix C of your textbook. All of this work has been done hundreds of years ago, well, 100 years ago. All of this work was done. There is no point in us reinventing the wheel. So I'm just going to slot my numbers in. The appendix tells me that the standard enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole. That's a number that we looked at just a minute ago. And I'm going to add to that twice the value of the enthalpy of formation of water. And the appendix tells me that number is negative 285. And then I'm going to subtract from that the enthalpy of formation of methane, which the appendix tells me is negative 74.8. And I'm going to add to that 2 times the enthalpy of formation under standard conditions of oxygen. Well, oxygen's an element, and an element in its standard state has an enthalpy of formation of 0. Okay, now I have a negative number, and I'm going to add to it another negative number, and then I'm going to subtract from it another negative number. So let's think about that for a second. Here's a negative number. I'm going to add a negative to it. Adding a negative is the same as subtracting. And then I'm going to subtract a negative, which is the same as adding. So negative 393.5 minus 570.8 plus 74.8 plus the 0 gives me a number that is negative 890 kilojoules. So for this particular reaction, that's the amount of heat that I get out. The enthalpy for this reaction is predicting a large negative number. Does that fit with what I'm expecting? Yeah, that's a combustion of a fossil fuel. We do that on purpose to generate heat. So I'm expecting this number for this reaction to be a large negative number. My answer is what I was expecting.